Let's continue and look at what happens with k-means when we change various parameters. So the next thing that we're going to change is the number of clusters. So our clusters are organized in a ring, and when we increase the number of clusters, we basically make the ring fuller and fuller until it really becomes, instead of a collection of blobs, a connection of Gaussians, it becomes a continuous ring. So let's see what happens with that. Okay, so here is the starting point, and here we have basically 4 well-separated clusters. And now we increased from 4 to 6, and we see that we have more clusters, but if we look at the reduction in the RMSE, we still can identify pretty nicely that 6 is the right number. Now we go to 8, and things become kind of smoother in the RMSE. So basically, it's not very easy to decide, is this at 6 or at 8? We know that it's 8 because that's what we generated. So it turns out that this is still enough data that the centroids fall right onto the centers. And so basically, we are recovering exactly the original centroids. So we're still in the good case. But now, if we increase from 8 to 16, we see that something becomes very messy, right? So we basically have our ring. We have a huge number of mistakes. And if we look at the centers, the green ones, they're not necessarily where the yellow triangles are. So there are some of them that are right on top of it, but some of them of the yellow triangles that are just in different places. So you might say, well, this is just a complete failure. But in fact, it is not so bad, because if we don't really care about the location, the exact location of the centers, but we just want to have the RMSE be low, then the RMSE actually falls down very nicely. It falls down, it continues to fall down beyond the large number of examples. But the thing is that if we start at 300, after we have 10 centers, we are somewhere around 20, which is very nice because we can use that for various things. So what can we use it for? So k-means, when people in electrical engineering talk about it, is basically thought of as vector quantization. So it's not really about finding the correct quote-unquote clusters, but simply partitioning the space into parts, and each part having a centroid associated with it, which is kind of the representative of that part. So this is something that we use a lot in compression and coding in electrical engineering. So in this case, we're not interested in whether the centroids are somehow related to the true source of the data, but we just want them as a codebook. We want something to use for compression. So the compression scheme is actually very simple. Once we've done, suppose that we have a lot of these data points that we want to transmit to another side, and we don't care if there's a slight error in the location. So what we do is we run k-means, so we find k-centers, and then we associate each example with the closest center, with the closest centroid. And then in order to transmit that to another location, we just need to transmit the index of that centroid, because we suppose that both the receiver and the sender have the same set of the same codebook. And so we send log2 of k bits that to the other side, and then the other side just identifies the centroid and uses that centroid as the message. Okay, so this is something that actually is used quite a lot in various devices. And if you want to see how it is used, for instance, to encode colors in a color space, have a look at this notebook. Okay, so let's continue. Next thing we're going to do is, in a sense, the most problematic one. We're going to increase the dimension. So what do I mean by increasing the dimension? the distribution that I showed you is necessarily a two-dimensional distribution because I can show it on the screen. But now I'm going to, for the real data that I'm actually using, have additional dimensions. And so while the centers are still just in 2 dimensions, each one of the clusters is a ball in d dimensions. Okay, so it's in a much higher dimension. And the question is, what will happen with k-means now? Okay, what would the dimension do to us? So the thing here is you're getting a little bit of a view into what happens in high dimensions and why high dimensions is so problematic. The first thing is that if you take 2 points in a Gaussian distribution, let's say, in high dimensions, then with very high probability, the 2 points have a particular distance between them. They have a particular distance, no closer and not further, okay? And so that is very strange. We're not used to that when we think about 2 dimensions. Like if we take random points in a Gaussian, they have various distances. But in high dimension, we have what is called concentration, and that means that every pair of points is very, very close. And so you can't really use things like nearest neighbors and so on. Okay. Another thing that we get is if we take the data that we generated, which is basically a ring, but a ring in high dimensions, and instead of projecting it onto the first 2 dimensions that we see, that's basically what we're going to continue doing, we just choose a random dimension and project it there, then the data will look exactly like single Gaussian. So basically the special dimension in which we see a ring is kind of disappeared. It's very hard to find it. It's basically somewhere in these many, many dimensions. Okay. And the last thing is that RMSE decreases with the number of centroids, but it decreases only extremely slowly. So basically, you can add more and more and more points to your k-means, but you basically are not improving the RMSE. And finally, k-means really breaks down. So what you get from k-means is not very useful. Okay, so here is our data. And here in this case, we have 500 points, 4 centers, and the radius is 2. So in this case, everything works very nicely. We see that there is very clear separation of the clusters. There are mistakes because the clusters are relatively close to each other, but the mistakes are where we expect them to be. So here is what we get when we have 20, dimension 20, and the number of examples is 500. And what we see is that, yes, it still works in the sense that the centers are close. But if you look at the reduction in the amount of error, it is not very much. Like if we basically look at the error, it reduced from 90 to a little bit below 80. Here it is scaled, so it looks very much the same as before. But if we look at it at the full scale, we see that it reduced very little. And now, if we go to even a larger dimension, so here we have a dimension of 500, and the number of examples is just 100, then everything breaks down, right? So we have basically more dimensions than we have examples, which is, in general, people expect it to never work. So, so what do we see here? What we see is that in terms of the reduction in the RMSE, it's almost unseeable. You know, it's very, very tiny. And if you look at it zoomed up, it's basically completely without an elbow, just kind of continuous linear reduction. And if we look at the examples and the mistakes, we see that they're all over the place. Basically, the centers are, as we expect them, in a square, but the centroids are all bundled up here in the middle. And you have to think that in other dimensions, they are basically up and down and everything. So they basically have nothing to do with the plane on which the 4 examples live, or the 4 centers live. Okay, so basically, at this ratio of dimension to number of examples, it is next to impossible to find any structure. Not to mention the structure of actually finding where the k-means are. Okay, so to summarize, we can measure the performance in various ways, but most ways require knowledge of the ground truth. So we know how the data was generated and we're trying to recover that. And that's almost never really the case when we want to use k-means. So the only measure that really stays with us even when we don't know the ground truth is the behavior of the RMSE. Okay? And we showed you how to use the RMSE to estimate the number of centers. So just as something to think about, can you think how to use it, the RMSE, to estimate whether a particular centroid is in the right location? Okay, so not saying that there is an exact answer to this, but in some situations you can do that very well. So just something for you to think and discuss. So some of the experiments we did, we saw that making the cluster closer makes the clustering harder. Decreasing the number of examples per cluster increases the error in the centroids, but doesn't necessarily hurt the labeling error or the RMSE. Increasing the number of clusters makes the distribution here into a ring, the way that we did it. And k-means will find some kind of good partitioning with a low RMSE, but it's not going to really relate to the original distribution. It's somehow just going to break up the ring into small parts that can be used in something like vector quantization. And when you go to high dimensions, that breaks k-means, right? So basically, if you're moving from data that you have at 10, 20 dimensions and you move to data that is at 1,000 dimensions, then you can expect a lot of trouble when you're using k-means. I'll see you next time.